Okay guys, so continuing from the previous video, we have left it at a cable subjected to uniformly distributed loads. Okay, so uh, please consider this cable. This is support 1 and this is support 2. This is your cable segment. Now you might have noticed that it is not in the straight segments, right? The entire cable is of a same shape because it is subjected to a similar kind of load, the uniformly distributed load. The difference between both the supports vertically is h, okay, and the horizontal distance between both the supports is l, h and l, okay. The y-axis and the x-axis are originated at this support. They are 0 0 here, and x is increasing in this direction, c, and y is increasing upward, okay. And w naught is the intensity of the load. uh, okay, we will discuss this thing further. Now, cables provide a very effective means of supporting the dead weight of girders or bridge decks having very long spans. Okay, so girders or the bridge deck, uh, for example, in the case of suspension bridges or the cable stayed bridges, the spans are very long and cables are very effective in supporting that load. A suspension bridge, for example, as I mentioned, is a typical example, and here I will mention you the name of Akashi Bridge in Japan. You can check it on internet. Okay, it is a suspension bridge, Akashi, Akashi. Please check it. It is a suspension bridge, and in which the deck is suspended from the cable using a series of close and equally spaced hangers. In order to analyze this problem, we will first determine the shape of a cable. Okay, so as you can see that the cable has been subjected to a uniform distributed load, and its shape is very important, that what kind of shape is it making. So first we will determine the shape of the cable, and keep in mind that the uniform horizontally distributed vertical load is applied. So the vertical load, and it is applied or distributed horizontally in a uniform manner. Okay, so horizontally it is uniform. Here the x y axis have their origin located at the lowest point. As I mentioned, that this is the origin point, such that the slope is 0 at this point and the slope is 0 at this point. Okay, if you draw a tangent, then its slope will be 0 with respect to this x-axis. Okay, and the free body diagram of a small segment of the cable having a length del s is shown in figure b. This is your figure b, and let me show you. For example, just consider this segment. See this one, the one that I highlighted, with the length of delta x, and this delta x length segment is located at a distance x from this origin. Okay, see this delta x length. This is the horizontal distance, or the horizontal segment of this total length del s. The total length, this portion, is delta s. Its horizontal projection is delta x, and its vertical projection is delta y. Okay, the the angle that this segment is making with x-axis, this is the line of x-axis. Okay, the angle that it is making at this side is theta, and the angle that it is making at the other side is theta plus del theta. What is delta? uh, we will discuss it further here. Just let me explain you different things. The tension in cable at this side is T, however at the opposite side it is T plus del T. So you are seeing that everything over here is different at that other point or other end, with some amount equal to delta multiplied by the original. Okay, this is W naught. See this uniformly distributed load, and when you multiply it with this horizontal distance, so W naught into delta x gives you a point load, and this point load will act at the middle, which is delta x by 2. from this point O. Okay, so now we know each and everything presented in this figure. Since the tensile force in the cable changes continuously in both magnitude and direction along the cable's length, this change is denoted on the free body diagram by delta T. So since the tensile force is changing along the length continuously, so the tensile force is T over here, and it is T plus delta T at this segment, and maybe at some other segment it will be T plus 2 delta T or something like that. Okay, the distributed load is represented by its resultant force, which is W naught delta x, as I explained you here, which acts at delta x by 2 from point O. Applying the equilibrium equations of equilibrium yields to, for example, summation of f of x is equal to 0, right? So let me remove all these things. Okay, so summation of f of x is equal to 0. So how many forces are in x direction? For example, this is one force, this is second force, right? So there are two forces that are acting in x direction, which is minus t. Why it is minus? Because it is in the leftward direction. So minus t into its angle cos theta, right? Here the angle is theta. However, the force at the other side is t plus delta t. So t plus delta t, and the angle is cos theta plus delta theta. So cos theta plus delta theta is equal to 0. This is your first equation. The second is summation of f of y. So summation of f of y, this is your first force in y direction, this is your second force in y direction, and this is your third force in the y direction. Okay, so minus t sine theta, c, it is downward, so it is minus. This one is plus, so it will be upward. Also this is downward, so this is minus. Minus w naught into delta x plus t plus delta t into sine theta plus delta theta. And the third equation of equilibrium yields that if you take summation of moment about point O is 0. So when you are taking moment about this point 0, so this force T plus delta T, as it is passing through this point, so its horizontal and vertical components will cause no moment because the perpendicular distance is 0. So it will be not included in this equation. W naught into delta x acting at a perpendicular distance delta x by 2 about point O. So this is our first moment, which is in counterclockwise direction, and it is positive, minus this t. It has two components, one is horizontal, other is vertical. So the horizontal one is causing the clockwise bending moment, see, so it is negative, and its perpendicular distance from this point to point O is delta y, right? And delta x, sorry, the vertical component t sine theta, it is causing counterclockwise, so it is positive, and its perpendicular distance is delta x, right? So you have gotten three equilibrium equations with the unknowns for t, delta t, delta x, delta theta. You are okay, delta y as well. So dividing each of these equations, for all these three equations, divide them by delta x. Okay, divide all of them by delta x, and taking the limit as delta x is approaching to 0. It means that delta x is very very small, so that it is approaching to 0. So if delta x is approaching to 0, then delta y will be approaching to 0, because it will be also too small, and delta theta will be approaching to 0 because it will also be too small, and delta t, the change in the tensile force, will also be equal to approaching to 0 because it will also be too small. So what we will be obtaining after that is, this is the first equation, d over dx of t cos theta is equal to 0, d over dx of t sin theta is equal to w naught. For example, when you solve these equations, you will get it. And the third one is dy by dx is equal to tangent theta. Now integrating equation 1, this is your equation 1, where capital T is equal to fh. This capital T is equal to fh, the horizontal force, okay, at x is equal to 0. This is your x is equal to 0. Okay, at this point your tension in cable is equal to fh. Okay, so we have t cos theta is equal to fh. So this is your established equation that at 0 0 your tension in the cable will be equal to reaction horizontal reaction at that support, which indicates the horizontal component or of force at any point along the cable remains constant. So it says that your horizontal component of force, since your cable is in like this, okay, like its parabolic shape, so its horizontal component will always remains constant at any point. Okay, please keep in mind. Now, integrating equation 2, this is your equation 2. Just integrate it, realizing that t sine theta is equal to 0 at x is equal to 0. This is your x is equal to 0. So it says that here all the forces are cos component. So sine theta is equal to 0 at x is equal to 0, since your theta is equal to 0, and when theta is equal to 0, uh, your sine is also 0. Gives t sine theta is equal to w naught x. This is your equation 5. Dividing equation 5 by equation 4, this is your equation 5. T sine theta is equal to w naught x, and this is your equation 4. T cos theta is equal to fh. You will get this sine over cos is equal to tangent and w naught x divided by fh. Right? This is your equation 6. Performing a second integration with y is equal to 0 at x is equal to 0 yields. See, this is your first boundary condition, that here when your x is 0, then your y is also 0. So when you integrate it, so you will get this y is equal to w naught to fh into x squares. Uh, since dx will go to this side and you will apply integration, so integration of a constant is y as you are doing with respect to y, and here this dx is coming here and you are integrating it with respect to x, so w naught divided by fh is constant, it will go outside the bracket, and you apply integration of x, so x square divided by 2 will be your integrated value, so y is equal to w naught x square divided by 2 fh. This is the equation of a parabola. See, so from here you know that the shape of the cable is now parabolic. The constant fh may be obtained by using the boundary conditions. For example, previously you have used that at x is equal to 0, y is also 0. Right? Now you can use this boundary condition that at this support, when x is equal to L, so your y is equal to h. Right? So it says that when y is equal to when x is equal to L, your y will be equal to h. Thus, putting this, you will get, for example, put x L in the place of x, and L in place of h in place of y. Okay, so you are getting this equation for f of h. And finally, substituting this into equation 7, this fh in this equation 7 gives you y is equal to h divided by L square into x square. Okay, from equation 4, this is your equation 4 that I highlighted. The maximum tension in the cable occurs when theta is maximum. Okay, so when theta is maximum, since it is a sine cos function, when theta is maximum, maximum tension will occur. For example, at x is equal to L, the theta will be maximum. Hence, from equations 4 and 5, we will get T maximum is equal to F square plus W naught L square. This is your maximum tensile force in the cable. Or using equation 8, where we can express Tmax in terms of W naught L under root 1 plus L by 2 H square. Okay, so you can use either equation 10 or equation 11. Now realize that we have neglected the weight of the cable, okay, in this analysis, which is uniform along the length of the cable and not along its horizontal projection. The weight of the cable is uniform along its length, okay, and the length is, as you know, it's parabolic, right, like this. But the load that we have considered, the UDL we have considered it that its horizontal projection is uniform. Okay, for example, let me show you again this one. Uniform horizontally distributed vertical load. Okay, so its horizontal projection is uniform, this one, but the cable itself, its load is uniform, and we have uh, ignored it in this analysis. Actually, a cable subjected to its own weight and free of any other loads will take the form of a catenary curve. However, if the sag to span ratio is small, which is the case for most structural applications, this curve closely approximates a parabolic shape as determined here. Okay, so from the results of this analysis, it follows that a cable will maintain a parabolic shape provided the dead load of the deck for a suspension bridge or a suspended girder will be uniformly distributed over the horizontal projected length of the cable. Hence, if the girder in figure A is supported by a series of hangers, you see this is a girder connected to a number of hangers, and the hangers are then connected to this cable, which are close and uniformly spaced. These hangers are uniformly spaced. The load in each hanger must be same so as to ensure that the cable has a parabolic shape. Okay, so in each hanger the load will be equal, no matter how long or short the cable or the cord is. Using this assumption, we can perform the structural analysis of the girder or any other framework which is freely suspended from the cable. So, a structure which is freely suspended. This is a structure that is freely suspended by this cable, and we are assuming it that it has a parabolic shape. Similarly, if the girder is simply supported, in the previous example, the girder was freely supported, freely suspended. Okay, no supports were there. But now consider that there are supports, for example, pin support and roller support or a rocket support are here, right? And this is a simply supported girder supported by the cable. The analysis will be statically indeterminate to the first degree. So there will be one unknown, and we will need one extra equation in the case of this kind of structure. Okay. However, if the girder has an internal pin, this is the same configuration of B, but only there is we have introduced an internal hinge at the middle. Okay, and as you know that introducing an internal hinge gives you an extra equation that summation of moment about this hinge is 0, right? So using this equation you can solve the your structure, right? Now coming to an example, it is example 2 because the example of point load that we discussed in the previous video was example 1. Since the lecture is same, so I have continued the numbering. The cable shown supports a girder. This is a cable from A coming to the lowest point, which is B, and then going up to the C, okay, which weighs 12 kilonewton per meter. Please note that the UDL, the uniformly distributed load, is applied 12 kilonewton per meter. Uh, Determine the tension in the cable at points A, B, and C. So you have to determine the tension at A, tension at B, and at C in the cable. Okay, this is your free body diagram. See, this is your tension at A, this is your tension at C, and somewhere here there will be tension at B, right? Now this is your lowest point of the cable, so you have taken this as a datum. Point C is 6 meter above it, and point A is 12 meter above it. Okay. Similarly, from this point B, you have divided the cable into two sections, one to the right and other to the left. So there are two segments AB and BC. Okay, so you have given the name of L dash to the horizontal projection of this cable BC, and since the total horizontal span is 30 meter, so this will be the 30 minus L dash, and this is the horizontal projection of segment AB. Okay, uh, at A it is making an angle theta A, and at C it is making a theta C, and at B the theta is equal to 0. You know the uniformly distributed load, which is 12 kilonewton per meter. Now consider the segment this one, right? Here you know that Tc is the tension at point C and T naught is the tension at point B, okay, which is the lowest point in the cable, which is 6 meter behind point C. Now the length of this segment is L dash, right? So your UDL is 12, and if you want to find its intensity, so 12 this UDL into total length, which is L dash, so 12 L dash is your total load that is acting on this cable, right? Now please note it carefully. As you know that dy by dx is equal to tangent theta, and in this case your tangent theta is equal to 12x1 divided by t naught. What is 12x1? Just consider this figure, right? So this is your t naught, which is this thing, right? This is your 12x1, which is your vertical load. Why I have used x1? Because if you go back, from this point, which we have considered as origin, going rightward gives you x1 and going leftwards gives you x2, okay. So therefore you have used x1 in instead of L dash. So your vertical component is 12x1, your horizontal component is t naught, this t naught, right? And your inclined component, this one, the resultant or the hypotenuse. So this theta, tangent theta is equal to perpendicular by base. Your perpendicular is 12x1 and your base is t naught. So integrating it with will give you this equation, and just ignoring the constants, you by solving this equation you will get t naught is equal to L dash square, okay. Please keep in mind that you have solved the equation in terms of x and then putting the values of uh, L dash instead of x1, okay. So this is your equation number one, where your T naught is equal to L dash square. Now going to the other segment, segment AB, which was 12 meter above this point B, the same thing. Here see, you have 12x2. Previously you had 12x1, right? Why? Because the load is same. Here you had x1, on the other side you have x2. So 12x2, and the T naught is also same, because at point B either you are coming from this side or this side, T naught will be same, right, at point B. So this is your base, this is your perpendicular, and Tx2 is your hypotenuse at this point. So using the same approach and solving this equation, you will get 1 is equal to 30 minus L dash square divided by 2 T naught. So this is your equation number 2. This was your equation 1 in terms of T naught and L dash. This is your equation 2 in terms of T naught and L dash. So you have two equations and two unknowns. You can easily solve them and find the values of L dash, which is equal to 12.43 meters, and T naught, which is 154.5 kilonewton. So this length is 12.43 and the remaining is 30 minus 12.43 is this length, this horizontal projection, okay. And you know T naught at this point, what is the value of tension? This is 154.5 kilonewton. So at point B, your tension in cable is 154.5 kilonewton. Now you know tension at B, you have to find tension at A and tension at C. So again, using the same approach, the same triangles that we used previously. See, for example, T naught and 12 L dash. Here it is TC. Previously it was tx1, right? So at this point, for example, tc, see, its base is this, and its vertical or the perpendicular is this. So your tc is the hypotenuse, 12 L dash or the vertical load or the applied load is your perpendicular, and the tension in the cable T naught is your base. So using Pythagoras theorem, you will find that the T at point C tension is 214.8, and using the same approach, tension at A is 261.4. So now you have determined the tension in cables at all the 3 points: tension at B, tension at C, and tension at A, right? So this was the analysis. Now the Another example that consider a suspension bridge. This is a suspension bridge where the cable is suspended, right? It is hanged or anchored over here, and through the hangers you have supported deck or truss or whatever system there is. So two stiffening trusses are there, right? Both are joined together at C and supported by a pin at A. Here is a pin support, and here is a rocker. Rocker is more or less equal, similar to that of roller support. Okay, determine the maximum tension in the cable IH. This is the segment IH. See, and you have to determine the tension in this segment. Okay, the cable has a parabolic shape. It is telling you itself that it is parabolic shape, and the bridge is subjected to the single load of 50 kilonewton. There is only one load, applied load, that is 50 kilonewton and applied at this point. Now please note that both the trusses are of same length, that is 12 meter. There are four spans of 3 meter, so this distance is 3 meter, this 3 meter, 3, 6, 9 and 12. Similarly 3, 6, 9, 12. Okay, so this is a 24 feet horizontal projection span. The vertical span is the lowest point of the cable is 8 meter below point H and I, and further the load is applied at 6 meter below this lowest point of the cable. Okay, so this is your configuration. Now coming to the solution, this is the left side of point C and this is right side of point C. See, this is your point C. You have divided the segment. This is left segment and this is right segment. Okay, now in the left segment, you know that at point I there will be IY, the Y component, and the X component, which is T naught. Similarly, this is tension in cable. Similarly, at H there will be a vertical component and horizontal component, which will be the tension in the cable. Similarly, the at middle there will be a tension in the cable, right? And at point C or point right above the point C, the tension will be same, T naught. Removing the supports, here was the roller support, so AY and AX, and here was the rocker support, so there is only BY, there is no horizontal reaction. Since point C was see, pin support, pin connected at their end C, right? So since it is a pin support, so it gives you vertical and horizontal reaction. And since you have taken the section at support C, so if you have taken downward in the left section, then the CY should be upward in the right section to maintain the equilibrium. Okay, so both the spans are 12 meter. C, the load is applied at 9 meter from BY and 3 meter from C. This is all your configuration. Now coming to the equation, summation of moment about point A is 0. When you are taking moment about A is 0, let me erase everything. Okay, when you are taking moment about A is 0, so this is your A point, and this force has 0 moment arm, this more force has 0 moment arm, this force has 0 moment arm, these forces has 0 moment arm, right? So all their effects will be neglected or ignored. Now what we are left with, for example in this case, we are left with only CY, right? So what is the distance of perpendicular distance of CY? 12. So minus 12 CY, because it is making clockwise movement. And the second thing, we are left with the T naught, T naught over here and T naught over here. So this T naught is making movement in the clockwise and its perpendicular distance is 6, right? However, this T naught is making movement into anti-clockwise and its perpendicular distance is 14. So 14 minus 6 is equal to 8. The resultant is 8 in the anti-clockwise into T naught. Got it? is equal to 0, and by solving it, it will give you that T naught is equal to 1.5 Cy. And similarly, you can solve it, but here you will get another moment due to this externally applied load C, 50 into 9. The rest is same. See, 12 Cy, 12 Cy, and 8 T naught. Only 50 into 9 is the new force, and by solving it, you will get T naught is equal to 1. Minus 1.5 Cy plus 56.25. Now you have got two equations and you have two unknowns, so using solving them, put T naught in this equation and you will get Cy is equal to 18.75, and using Cy here you will get T naught is equal to 28.125. So you know both the values, you got the value of T naught. Okay, now you have to solve it at I and at H, that what is the value. Now from 1 and 2, Cy is equal to this and T naught is equal to this, we saw on the previous slide. As we know that the left section has this configuration, now we know this T naught. Okay, to know this T1 or Ti, we need to know this theta I, and to know this theta I, we have to know the geometry. For example, the Tx or Ti is a hypotenuse, the base is this T naught here, right? And the perpendicular is this vertical hanger force, which is W naught into X, right? So using again the same equation of tangent theta, which is equal to perpendicular by base, and integrating it with respect to X, we will get this thing, cancelling again the constant, it's assuming it is 0. Putting the values, we will get W naught is equal to 3.125 kilonewton per meter is acting downward. Okay, now we have two segments, T naught in at point B. We know what is the value of vertically applied load, or the load that is suspended with the cable, from the cable. So we have unknowns Ti and we have unknown Th, both at I and H point. We don't know the theta I and theta H. Okay, so using their trigonometry for theta I, we know the perpendicular, we know the base. So use perpendicular over base and you will get theta I. Similarly, use Pythagoras theorem and you will get Ti. Here Ti is 46.88 kilonewton. Using this equation or this configuration, you will get the same value of Th, which is 46.88 kilonewton. So previously the value of T naught was 28.12. However, here the value of Ti and Th is 46. So this is the maximum value, which is 46.88. So Tmax is 46.88, which is at the points I and H. And the minimum value is here, because here the slope is maximum and here the slope is minimum. Okay, and as you have determined W naught, so multiply it by 3. Why multiply it by 3? Because you know the span between each hanger. For example, this vertical cable or vertical hanger, they are connected to the cable. So the distance between them is 3 meter. So multiply W naught and you will get the force on each cable. So that is 9.375 kilonewton load that is acting along each hanger. Okay, now summation of moment about A is 0. We have 9.375 force of each one and is acting at 3, multiply by 3, plus this force multiply by 6, multiply by 9, multiply by 12, multiply by 15, multiply by 18 and 21. So see, we have these vertical forces effect, right? Also we have this applied load 50 kilonewton at a distance of 15 meter, and we have this By multiplied by 24. So from here we will get the value of By, which is minus 1.56 kilonewton. Simply using summation of f of y, there is Ay, there are these 7 forces, 7 into 9.375, there is this 50 kilonewton downward. So from solving this equation, you will get the value of Ay minus 14.07 kilonewton, and it is acting downward. Okay. Now coming to the next example, uh, another uh, uh, cable subjected to a uniformly distributed load. For the structure shown, determine the maximum tension of the cable. Okay, now you have to determine maximum tension in the cable and draw the quantitative shear and bending moment diagrams of the beam for this beam. So that will be your homework, to draw quantitative shear force and bending moment diagrams for this beam. Now keep in mind that there is an internal hinge at point B. Okay, the lowest point, for example this point, is 8 meter below support E, and it is 0.5 meter below support D. Okay, and below this lowest point the girder is at 8 meter, right? So coming to the solution, the free body diagram, uh, please keep in mind that the lowest point, or the B, this is at 5 meter, okay, from support D, and 20 meter from support E. Okay, now this 5 meter horizontal projection with the zero point 0.5 meter vertical projection using 1 kilonewton per meter and multiply it with 5 meter, so gives you a 5 kilonewton force acting at this segment, right? Now the unknowns are dy here, since it is a hinge support, so there will be upward and sideways. So the lateral is T naught, that as we know from previous concepts, that the reaction will be equal to the tension in the cable in the horizontal direction. We have to know the D naught. Similarly, the T naught in the cable at the lowest point. Also, as this is a hinge support, so there are two reactions, the vertical reaction and the horizontal reaction. So AY and AX at this point. Similarly, point B is a hinge, so BY and BX need to be determined here, right? Now taking summation of moments at A equals to 0. So when you take moment at A 0, so your AY is multiplied by 0, AX is 0, BX is 0 since it is passing through point A, your DY is 0 since it is passing through point A. So what you are left with is this BY and this T naught. And if you remember that from previous example, this T naught will have different effects. For example, this zero point 0.5 and this 8. Okay, so this 8 will act clockwise, and this 8.5 will act counterclockwise. So this will cancel out from this, and we will left with zero point 0.5 in clockwise counterclockwise direction. Okay, so solving this, we will get By is equal to 0, which means that there is no vertical force in it, and T naught is equal to 25 kilonewton. So the tension in the cable is 25 kilonewton. Now taking the longest segment, which is this one, this 20-meter segment, okay, from this point to this point, we know the 20 into W naught. Why? Because the span length or horizontal projection is 20 and the load is 1 kilonewton per meter, so it is 20 into W naught. And we also know the T naught from previous slide, which is 25 kilonewton. So T naught is our base in this triangle, and W naught X is our perpendicular, right? And we know the value of W naught. We don't need to use this equation this time because we already know W naught. So just put the value of 20 into W naught, which is 20 kilonewton. You know the value of T naught, so you will get the maximum value at support E. So TE is equal to 25 square plus 20 square under root is equal to 32.02. This is our maximum value of tension in the cable. Likewise, as you know that there are 9 hangers. For let's count it: 1, 2, 3, 4, 5, 6, 7, 8, 9. So if there are 9 hangers, then there are 10 spacings. For example, this is one spacing, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So there are 10 spacings and the total vertical load is 1 multiplied by 25. 25 kilonewton is acting downward, right? And I want to divide it in 10 equal, so 25 divided by 10 gives you 2.5. So 2.5 is the amount of load that each hanger is carrying, right? And at B you have seen that there is no force. See, By is equal to 0. So simply using the equations, using moment about A is equal to 0, you will find Ay, and then summation of f of y, and you will find Cy. Please note that there is no horizontal force in the structure, so Ax is equal to 0. Drawing its your force diagram and drawing its bending moment diagram, which was required. So this is the solution of cables subjected to different types of loading. These are the references. Structural analysis by R.C. Hibbeler. Its 8th edition was used in the preparation of these lectures. And thank you very much.